Hello everyone, I'm Derin Dalçık and my teammates are Yusuf Çağançelik and Eren Gencol and we are Group 1. And today we will be presenting our mechanical design senior year project which is called ShopBot. The goal of this project is to design a shopping cart that can autonomously follow a user so that they don't need to push or carry weight while shopping. We aim for smooth, stable and collision-free motion even in crowded indoor environments. To achieve this, ShopBot uses camera-based human detection and LiDAR-based obstacle sensing, while the control system adjusts the wheel speeds to keep a safe following distance. Here you see the first proposed mechanical design of our prototype. We created this CAD model to define the overall structure, geometry and component layout of the robot. And here you can see the final design. At the bottom, we designed an aluminum base plate measuring 50 by 70 centimeters, which carries the full weight of robot and supports the motors, battery and electronics. Above it, there is an electronics compartment with a height of 35 centimeters, where the controller is mounted on plexiglass to avoid Faraday cage effects and ensures reliable sensing. On the top, there is a storage basket with a base of 60 by 40 centimeters and a height of 32 centimeters, where the user's items are carried. Under the chassis, 4 DC motors drive the wheels. We designed and 3D printed custom motor holders to keep the motors rigid and properly aligned. Originally, we planned to use standard wheels, but we switched to mechanism wheels to improve maneuverability, making turning and navigation easier in narrow aisles. At the front of the robot, we designed a sensor mesh to mount to camera and LiDAR, giving them a clear field of view for detection and obstacle sensing. Overall, the CAD model focused on stability, balanced weight distribution, and clear sensor visibility, forming the mechanical foundation of our system.
Structural analysis was performed in ANSYS to evaluate the mechanical integrity of the shopping cart chassis under realistic loading conditions. The applied load represents the combined weight of all on-board components, including the motors, electronics, and the battery, while the base of the chassis was fixed to simulate ground contact. Based on the analysis requirements, aluminum was selected as the chassis material due to its high strength-to-weight ratio, and the chassis thickness was determined to be 3 millimeters. The resulting von Mises stress distribution shows higher stress concentrations in the central region of the chassis. This behavior is expected as the heaviest component of the system, the battery, is positioned at the center of the chassis to ensure balanced weight distribution and system stability. Even in these critical regions, the maximum stress value remained well below the yield strength of aluminum, indicating that the structure operates entirely within the elastic region. Total deformation results show a slight increase toward the edge of the chassis. This trend is attributed to the additional loads and upward reaction force generated by the motors in a moving system, which act together with the overall structural load. Despite this effect, deformation values remain extremely small and visually negligible. Overall, the ANSYS analysis validates both the selected material and thickness, confirming that the chassis is mechanically safe and suitable for real-world indoor operation.
This slide shows the overall system architecture. The system consists of two main units, a laptop and a Raspberry Pi. The camera and LiDAR are connected to the RPi, which streams camera data to the laptop. On the laptop, YOLO is used to detect a person and compute motion decisions. These high-level commands are sent back to the RPi. The RPi checks safety using LiDAR data and drives the motors. In summary, perception and decision-making run on the laptop, while safety and actuation are handled on the RPi. This slide explains how distance is estimated using a single camera. Since we use a monocular camera, depth cannot be measured directly. After YOLO detects a person, we measure the bounding box height in pixels, denoted as h. This value is inversely related to the distance. To calibrate this relationship, we record the bounding box height at known distances of 1 meter and 2 meters. From these 2 points, we derive a simple model. The distance is estimated using the equation distance equals to a divided h plus b, where a and b are calibration parameters. We can see how motion decisions are computed on the laptop. YOLO itself does not control the robot, it only provides measurements. From the detected bounding box, we compute two error terms. The first is the distance error, which represents how far the person is from the target distance. The second is the horizontal error, which indicates whether the person is centered in the image. Based on these errors, the system decides whether the robot should move forward, stop, strafe, or apply a yaw correction while moving. These decisions are sent to the RPi as structured commands. And we can see how RPi executes the received commands. Before moving, the RPi checks LiDAR data to ensure the path is safe. If an obstacle is detected, the robot slows down or stops. If the environment is safe, the command is converted into a velocity vector consisting of forward, lateral, and rotational components. This velocity vector is mapped to the individual wheel speeds using omnidirectional kinematics. The resulting motor commands are applied using PWM signals. In this way, the RPI enforces safety and converts high-level decisions into physical motion.
Here you can see a demo of our prototype. In conclusion, we successfully designed and built an autonomous shopping cart that can follow a user indoors using camera-based detection and LiDAR sensing. The prototype demonstrates stable and flexible motion with mechanism wheels. For future work, the project can be adapted to the system for real-world retail environments with large-scale user testing, and add voice or app-based user interaction to improve stability. Thank you for listening.